Hello everyone, this is Dr. Vignesh Farmeka, Assistant Professor of Geography, Government Degree College for Women's Autonomous Headley. In this chapter, the wind system, we are going to cover the following points. The present session discusses about introduction to wind, Headley cell, Ferrel cell, polar cell, and measurement of wind movement and factors affecting wind. Firstly, we will look into introduction to winds. Global winds blow in belts encircling the planet. The global wind planes are enormous and the winds are relatively steady. These winds are the result of air movement at the bottom of the major atmospheric circulation cells, where the air moves horizontally from high to low pressure belts. Technology today allows anyone to see global wind patterns in real time, such as Earth wind map. The pattern of the movement of the planetary winds, that is permanent winds, is called the general circulation of the atmosphere or air circulation. The general circulation of the atmosphere also sets in the motion the ocean water circulation, which influences the Earth's climate. Air attempts to balance the uneven distribution of atmospheric pressure. Hence, it moves from high pressure areas to low pressure areas. Here we discuss about the two terms, wind and air current. Wind, the horizontal movement of air from high pressure areas to low pressure areas, is called wind. Air current, vertical movement of air either upward or downward, is called air current. Both winds and air currents from the system of circulation in the atmosphere. Now, we will discuss about the Headley. The air at the equatorial low pressure belt rises because of the convection currents. The air reaches the top of the troposphere up to an altitude of 14 kilometers. And moves towards the poles. This causes accumulation of air at 30 degrees north and south latitudes. Part of the accumulated air sinks to the ground and forms a subtropical high. At the surface, a compound of the diverging wind from the subtropical high pressure belt flows towards the equatorial low pressure belt as the easterlies, that is from the northeast to the southeast. The easterlies from either side of the equator converge at the equatorial low pressure and the cycle repeats. Such circulation of winds is called a cell. Such a cell in the tropics is called Headley cell. The figure on the screen discloses you about the Headley cell, the Ferrel cell, and the polar cell. The Headley cell at the equatorial region, the Ferrel cell in mid-latitudes, and whereas the polar cell in the high latitudes. Now, the Ferrel cell. In the middle latitudes, the circulation is that of sinking cold air that comes from the poles, and the rising warm air that blows from the subtropical hydrogen belts. At the surface, these winds are called westerlies, and the cell is known as the Ferrel cell. In the middle of the picture on the screen discloses you about the Ferrel cell. Next, polar cell. At polar latitudes, the colder and denser air subsides near the poles and blows towards middle latitudes as the polar eastwards. This cell is called the polar cell. And these three cells are the pattern of the general circulation of the atmosphere. The transfer of heat energy from lower latitudes to higher latitudes maintains the general circulation. Measurement of wind movement. Just like wind speed is measured by an anemometer, wind direction is measured by a weather vane or wind. And wind has direction and speed. And speed is measured by anemometer and direction is measured by the wind or the weather. It is possible to use multiple wind vanes spreads across many locations to determine the broader wind profile of a geographic region, especially if they are installed along with anemometers. The combination of an anemometer and a wind vane mounted together is often called as an aero vane. Once wind direction is measured, it can be reported in the cardinal directions or degrees. The picture on the screen is the anemometer and is used to measure the speed of the wind. And the picture on the screen discloses you the weather vane or the wind vane. It is used to find out the direction of the wind flow. Cardinal directions. It is important to note the direction from which the wind is blowing. For example, a westerly wind blows from west to east. Degrees. Alternatively, the wind can be reported in clockwise, degrees counting from the north, which corresponds to 0 or 360. Thus, 90 degrees is equivalent to the east, 180 degrees is equivalent to the south, and 270 is equivalent to the west, whereas the 360 or 0 is equivalent to the north. The first wind vanes served mostly a decorative purpose rather than being a meteorological tool, and rooster-shaped wind vanes are common in European churches, given that the rooster is associated with the Saint Peter. Wind direction measurement can also be used for recreational purposes, it is used in both golfing, boating also. Factors affecting wind movement. The wind refers to horizontal movement of air, whereas air current refers to vertical movement of air. Now, here we shall discuss about the factors that affect the movement of the wind. And they are the pressure gradient force, the beyond force, the frictional force, the Paralysis force, the gravitational force, and the centripetal force. Firstly, we will look into the pressure gradient force. The pressure gradient, that is the difference in pressure distribution between atmospheric pressure cells and the surrounding, causes the movement of air from relatively high pressure centers to relatively low pressure centers. This motion of the air is called as wind. Greater the pressure difference, greater is the wind speed. Small differences in pressure are highly significant in terms of the wind direction and velocity. The pressure gradient is strong where the isobars are close to each other and is weak where the isobars are apart. The wind directions follows the direction of pressure gradient, that is perpendicular to the isobar. The figure on the screen discloses you the pressure gradient force. When the pressure gradient is steep, the wind velocity is higher, while the weak pressure gradient causes the wind to blow at a low speed. The spacing of the isobars is a measure of the amount of pressure change occurring over a given distance. The same is expressed as the pressure gradient. Pressure gradient is steep when the rate of change is great, while it is said to be weak when the rate of change is small. Therefore, the velocity of the wind can be estimated from the spacing of isobars. Closely spaced isobars mean a steep pressure gradient and high velocity winds. Widely spaced isobars, on the other hand, indicate a weak pressure gradient and light winds. The next is beyond force. The atmospheric pressure cells also determine whether the air sinks or rises at a place. The surrounding atmosphere exerts beyond force on low pressure cells, and hence the air within a low pressure cell rises, as it shown in the figure that appears you on the screen. On the other hand, the air within a high pressure cell sinks as it is denser than the surrounding atmosphere. Rising air is associated with convergent and unstable weather, that is cyclonic conditions, whereas the sinking or subsiding air is associated with divergence, and stable conditions, that is anticyclonic conditions. A rising pressure indicates increasing stability, while a falling pressure indicates the weather becoming more unstable. The converging wind movement around a low pressure is called the cyclonic circulation, and a high pressure, the wind divergence, and the movement is called the anticyclonic circulation. The wind circulation at the Earth's surface is associated with an exactly opposite wind circulation above in the upper troposphere. Apart from the convergence, convection currents, orographic uplift, and uplift along fronts cause the rising of air, which is essential for the formation of clouds and precipitation. The next is the frictional force. The irregularities of the Earth's surface resist the wind movement in the form of friction. The influence of friction generally extends up to an elevation of 1 to 3 kilometers. Over the sea surface, the friction is minimal, while on the continents, that is in the rugged surface, it is maximum. At the surface, due to the high friction, the wind direction makes high angles with the isobar on the maps. The next is Paralysis force. Due to the Earth's rotation, winds do not cross the isobars at right angles as the predicted gradient force directs, but get deflected from their original path. This deviation is the result of the Earth's rotation and is called the Paralysis effect. Due to the Paralysis effects, wind in the northern hemisphere get deflected to the right side of their path, and those in the southern hemisphere to their left side. That is also called as the Ferris law. This deflection force does not seem to exist until the air is set in motion and increases with wind velocity and an increase in altitude. The Paralysis effect. The Paralysis effect is apparent deflection of objects such as aeroplanes, wind, missiles, sniper bullets, and ocean currents moving in a straight path relative to Earth's surface. What are the causes of the Paralysis effect? As the Earth spins in a counterclockwise direction on its axis, any object flying over a long distance appears to be deflected. This occurs because as something moves freely above the Earth's surface, the Earth is moving east under the object at a fast speed. As the object moves away from the equator, the speed of the Earth's rotation decreases and the Paralysis effect increases. A plane flying along the equator itself would be able to continue flying on the equator without any apparent deflection. A little to the north or the south of the equator, the plane would be deflected. Next, the geostrophic wind. The Paralysis force acting on a body increases with the increase in its velocity. The winds in the upper atmosphere 2 to 3 kilometers above the surface are free from the frictional effect of the surface and are controlled by the pressure gradient and the Coriolis force. When isobars are straight and when there is no friction, the pressure gradient force is balanced by the Coriolis force and the resultant wind blows parallel to the isobar, that is, deflection of the wind is maximum. And this wind is known as the geostrophic wind. The next is centripetal acceleration. It acts only on air that is flowing around the centers of circulation. Centripetal acceleration creates a force directed at right angles to the wind movement and inwards towards the centers of rotation. This force produces a circular pattern of flow around centers of high and low pressure. The figure on the screen discloses you the centripetal acceleration. So far, we dealt with introduction to wind, measurement of wind movement, Headley cell, Ferrel cell, polar cell, and the factors affecting the movement of the wind. In the next session, we will focus on the classification of winds.